My name is Hoang and my partner Joosuk. Today we're here to talk to you about binary frequency shift keying. In binary frequency shift keying, better known as BFSK, we are here to demonstrate how random processes relate to a simple case of BFSK communications and demonstrate the effects of additive white Gaussian noise. We also discuss the relationship between spectral density, spectral energy density, power spectral density, signal-to-noise ratio, and autocorrelation. In most media used for communications, only a fixed range of frequencies is available for transmission. As a result, transmission of data by FSK modulation is done, although many other forms of digital modulation are available as shown. Here's a block diagram of BFSK modulation and coherent demodulation. Okay. FSK is the changing of transmission based on the information of the message signal. In the binary FSK case, a 1 is called the mark frequency, and a 0 is called the spaced frequency. In this case, in the following case, we have 3 Hz and 10 Hz signal, as you can see there. When the digital signal is a 1, the modulating frequency is 10 Hz. If it's 0, and we have only 3 Hz. Next, we have the relationship between energy, power, and autocorrelation. As you can see here, energy is measured from infinite amount of time, as opposed to power, which is time average of the energy. Next, my partner will discuss the results of our simulation.
Alright, now I'll talk about the results. As you can see here, here's your modulating signal, and using the bit pattern provided to us here, shown here, we have modulated the signal, as you can see here. And after this signal has been transmitted, it will gain the noise, and we have simulated this by adding the additive white Gaussian noise. And after the noise has been affected, you can see that amplitude has decreased and both of the signal has been affected by the noise. Next, I'll talk about the spectrum of the modulated signal. As you can see here, before the noise, the spectrum peaks are very strong, and you can see the clear peaks at the 3K and a 10K. However, after the noise has been affected, you can see that noise increased and the amplitude has decreased, and the peaks are very thinner than usual. Next, I'll talk about the bit error rate versus the SNR. As you can see here, here's the noise and here's the signal. And when the noise is decreased, you can see the SNR will increase, and if noise is increased, the SNR will decrease. Okay. Alright, since we're dealing with the digital signals, we cannot do the Fourier transform. So in order to do that, we have to go through the autocorrelation. As you can see here, when we do the autocorrelation of the original signal, it's very clear signal and very strong signal. However, after the noise has been affected, you can see that the signal has very low correlations. And doing the Fourier transform of this autocorrelation, you will get the power spectral density. As you can see here, there's also, you can see the peak at 3K and 10K. However, after the noise has been affected, it's very difficult to see where it is, but here's the peak right here, those 2 peaks that have been mentioned before, and a lot of noise has been affected by it.
And that concludes our presentation. Thank you.
Thank you.